morning all. My name is B. Santhosh Kumar, Assistant Professor, Institute of Aeronautical Engineering. My subject is Computer Architecture. Today I am discussing about a simple instruction set architecture. So, in a simple instruction architecture, the designing of the instruction set architecture is the most important in the design of a microprocessor. A poor designed ISA, even it is implemented well, leads to bad microprocessor. A well-designed instruction set architecture, on the other hand, can result in a powerful processor that can meet variety of needs. So, when the designing of ISA, the designer must evaluate the trade-offs in performance and such constraints issues as size and cost when designing and specifications. A good way to start designing an instruction set architecture is to decide what you want to have when you finish. Okay, so instruction means, suppose I have to go for the arithmetic addition of two numbers. So what are the instructions I have to give? Add ax comma bx. So what is the meaning? Means I am doing the operation. What is the operation? I am doing the addition operation. So what are the registers I am taking? Here I am taking registers. How many registers I am taking? A comma b. So in this instruction, which operation you are performing, that is showing in a operation. Okay, it is one instruction. This instruction has add ax comma bx or sub ax comma bx. Okay, so whatever maybe you are taking the instruction, so it will be showing us which operation you are performing. So that is the important one. So your instruction is showing which performing of your operation. So the instruction set architecture is the most important of the design of a microprocessor. A poor designed implemented well leads to bad microprocessor. Okay, suppose your instruction is, you are not giving any clarity about this one. So how can it will be implemented? Okay, it is called poor designing of instruction in the microprocessor. And the instruction set architecture, on the other hand, can result in a powerful processor that can meet variety of needs. In designing of ISA designer, ISA means a simple instruction architecture. So it must be evaluate the trade-offs in performance as such constraining issues as size and cost when designing ISA specifications. A good way to start designing an instruction set architecture is to decide when you want to have you finish. Okay, so it will be finishing. Suppose I am taking after the completion of Z into 03. So interrupt 03 means I am completing my program. Okay, I am completing my operation. So how can you? It depends on your performance of your instruction. It will be showing your execution of the program. So that is the important one. And processor to be used for general purpose computing, specialized processor. Okay, so which type of operation you are performing, which type of microprocessor you are using, okay, which purpose you are using. So processor to be used, which processor you are using and what is the processor is helpful for this one. Okay, general purpose computing, specialized processor. Okay, so we'll discuss what is general purpose and what is specialized purpose. So the issues of completeness of the ISA is one of the criteria in designing the processors. That means the processor must have complete set of instructions to perform the task of the given application. Another criteria is instruction orthogonality. Instructions are orthogonal if they do not overlap or perform the same function. Suppose I am taking one example, a microprocessor with 10 different instructions that perform the exact same function of jump. Okay, here taking one example is jump. Okay, jump means we are operating one performance to another. Okay, one operation to the another operation. Okay, one block of memory register into the another block. Okay, so the issues of completeness of the instruction set. The criteria is designing the processor. That means the processor must have complete set of instructions to perform the task of the given application. In that instruction, orthogonality and instructions are orthogonal. They do not overlap or perform the same function. Okay, so we can't perform the same operations. Why? Because if I am performing the same operations, it will be which operation can be performed now for present. It will be confusing. Okay, so if I am taking the jump operation, okay, in this operation the instruction perform the exact same function. When going for the jump, it will be jump to one memory to another memory, or one register to another register. Okay, so the instructions are major role in the operations. Okay, suppose I'm taking add ax comma bx, sub bx comma cx, move ax comma bx, and int 03, rotate left. So when I'm going like this operations, okay, jump function, call, okay, shift, okay, shift right or shift left, right, like this. So when you are, it is one operation, okay, one operation. So in this add, okay, I'm taking as a operand and operator. Okay, what is the operand means? Sub. What is operand means? Add. What is operand means? Move, int, jump, call. Okay, these are the operand. Operators means I'm taking ax comma bx are the two registers, bx comma cx are the two registers. Okay, like this. How many registers we are taking? Okay, that is the important one. So when and how many registers you are taking? Okay, that is the operand or operation. Here, how many operands are there means two operands. Suppose I'm taking add ax comma bx comma cx. Okay, how many operands means operands means three operations are three operands are there. Okay, so these are the registers or whatever maybe you have to take, but the complete operation is called one instruction. Okay, it is called one instruction. So another area in which the designer can optimize the instruction set architecture is the register set. The registers have a large effect on the performance of a CPU. The CPU can store data in its internal registers instead of memory. The CPU can retrieve data from its registers much more likely than from the memory. Having too few registers causes a program to make more reference to the memory, thus reducing the performance. Okay, so when we are going for the instruction set architecture in the register set, okay, register set R1, R2, so on, register set. So the registers have a large effect of performance of a CPU. Suppose I'm taking R1 equal to some 0 to 15, like 16-bit register. Okay, I'm taking R2 is a 8-bit register. Okay, and I'm taking R3 equal to some 4-bit register, like this. Okay, so the registers have the large effect of the performance of CPU, and the CPU can store the data in its internal register instead of memory. Instead of memory, I'm taking the internal register. Instead of memory, I'm not taking memory, I'm taking only the registers. Okay, so in the memory, what is a memory means? Set of registers. So in the set of registers are storing storing in the memory. Okay, so in the register, which type of, suppose in the register, suppose I'm taking, it is a 4-bit, I'm taking 1100. Shall we call is it data? Yes, it is a data. Which data means 4-bit of data. Okay, this 4-bit of data is stored in a register. Okay, so set of registers are in a memory. Okay, so the CPU can store data in its internal registers instead of memory. Okay, in place of memory, I am using registers. So set of registers I am taking as a memory. In that registers, what will be stored means the data will be stored. The data is in the form of binary, and the CPU can retrieve data from its registers much more likely than from the memory. Having too few registers causes a program to make more reference to the memory, thus reducing the performance. So if I am taking the few registers in the program to make more reference to the memory, thus they are reducing the performance. If I am taking the less registers, what will happen? I am taking less registers. So when I am taking the less registers, it will be causing as a memory, causing to be reducing the performance of the CPU. Okay, so instruction set architecture, ISA. The instruction set architecture is the part of the processor that is visible to the programmer or compiler writer. The ISA serves as the boundary between software and hardware. We will briefly describe the instruction set found in many of the microprocessors used today. The ISA of a microprocessor can be described using 5 categories. Okay, so I'm talking about the instruction set architecture. So what is the functionality and what are the advantages and applications we'll discuss. The instruction set is a part of the processor that is visible to the programmer or compiler. Programmer or compiler means I'm the programmer, I'm writing one program. Okay. So this programmer or compiler is writing. Okay. After completion of the program, I'm going for the compiler and execution. So ISA instruction set architecture as a boundary between the software and the hardware. It is between the software and the hardware. So the ISA of a processor can be described using the 5 categories. So operand location, can any ALU instruction operand be located in memory, or must all operands be kept internally in the CPU? Okay. First, what are the 5 categories of ISA instruction set architecture? Those 5 categories we'll discuss. First one is a operand location. Okay, already we know that add AX, BX. So operand location. Can ALU instruction operand located in memory, or must be operand kept in internally of the CPU? So it will be kept in the CPU or in the memory. Operations. What operations are provided in the ISA? Type and size of the operands. So what is the type of and size of the operand and how it is specified? All of the most distinguished factors in the first, the most 3 types of ISA means instruction set architectures. Stack, the operand are implicitly on top of the stack. Accumulator. Okay, I'm taking instead of operand. Which operand I'm taking means first one is a stack. After then accumulator ACC. So this stack operand is implicitly on top of the stack. Okay, in the top of the stack it will be implemented. It is one type of operand. And next one is a accumulator. It is a very important. So one operand is implicitly the accumulator. Okay, when I'm taking only one operand is implicitly the accumulator. Okay, and another one is a general purpose registers, GPR. All operands are explicitly mentioned. They are either registers or memory locations. General purpose register, GPR. All operands are explicitly mentioned. They are either registers or memory locations. They are either registers or memory locations. Or memory locations. Okay. So these registers and memory locations are under the operand. Okay. So stack, accumulator, and general purpose registers. Okay. So what is the operand? This operand is stored in a memory or in CPU. Okay. So maybe this is the arithmetic logic unit, logic operations are be there. Suppose I'm taking operand is a add, sub, div, like this. So maybe these are the ALU, arithmetic logic operations are there, or we are taking not only arithmetic logic operations, we are going for the shift operation. We have to jump, call like this operands, and maybe these are stored in the memory or in CPU. And operator means these operators are in a registers. These are stored in a registers and memory. Okay, so let look at the assembly code of C equal to A plus B. I'm taking one operation C equal to A plus B in all 3 architectures. Okay, I'm going for the first one is a stack, second one is an accumulator, third one is a GPR. In the stack, what will happen? Okay, I'm taking operation C equal to A plus B. First, what is operation means? First step, push A means I'm taking call. First, I'm taking register A, that is a push. and another one is a push B, means I'm taking the another register, that is the B, and add, it is the arithmetic logic unit. I'm taking a operand. I'm taking the operand. Add pop C, means after the addition, what will be stored? The addition of two numbers, A plus B storing in C, that is a pop C. Suppose I'm taking A equal to 5 and B equal to 3. So what is operation here? C equal to A plus B. That means 5 plus 3 is equal to 8. What is C equal to 8 or not? Yes. In the 5 values in storing in A, and B equal to 3 and C equal to how much? 8. So that is pop C. So in the C register, what is the value? 8. So the resultant value is stored in C. And accumulator is a load A, means I'm taking one register A, add B. Add B means addition of B with which one? A. Why? Because load A. Already I called this function. Okay. It is like a call function. Okay. So add B means add B means, that means add A comma B. That means why? Because add B is there. Where is A? A is loaded already. Loading function. Okay. Loading means already the register is waiting for which one? For operand. Which operand? And here add. So add B means add B comma A. Which one? Already load A means A is ready for operand. And store C means after the addition of A comma B, the value will be stored in C. C is nothing but A plus B. Already we know the A value and we know the B value. C equal to result of A plus B. So the final resultant value storing in C. So here it is somewhat, it is different. Here GPR, general purpose registers, means I am taking load R1 comma A, means A value, the value of A register storing in R1 and B register value is storing in this one. Next, store R1 comma C. That means load. See here load R1 comma A. Already we know that what is the A value? A equal to 5. So this A equal to 5 is storing in R1. So R1 equal to 5. This B value, suppose I am taking 3. Add, we can observe properly this one. Add, what is R1 here? R1 equal to 5. What is the B value? B equal to 3. So add 5 comma 3. So storing in C equal to A plus B. So that is C equal to 8. So the C value is 8. Is storing in R1. So finally where is storing? R1 equal to 8. Why? Because R1 is a resultant value. Okay. So we can observe here in the stock value, push A means A equal to 5. Push B means B equal to 3. And add means addition of two numbers. So A equal to 5 and B equal to 3. Added. The resultant value stored in C. That is the pop C. Pop C means result of C. That is the stack. So here I took the, which operand I am taking? Push. What is operand? Push operand. Here I am taking load, add. These are the different operands are there. So load A means A, suppose I am taking A register, the value A equal to 5. And add B means add B is there. Adding with which one? Already the loaded value is there. Now we are calling this load value and added with B. So A equal to 5 already we know and B equal to 3. Stored in C. Store C means the result of A comma B is storing in C. So general purpose register means load R1 comma A. That means A value is storing in R1. So what is the A value? A equal to 5. Storing in R1. That means R1 equal to, here R1 equal to 5. Here add R1 comma B means already R1 value equal to 5. B I am giving as a 3. 5 comma 3 means add 5 comma 3 means I am adding the 5 and 3. So added means 5 plus 3. Where it is storing? Already we know that C equal to A plus B. So the value of C is storing in A plus B. C equal to A plus B. So C equal to 8 means storing in R1 comma C. C equal to 8 value is there. It is storing in R1. So it is the GPR. So there are three types of instructions are there. Three types of architectures are there. Stack, accumulator and GPR. So what is the stack advantages? Simple model for expression evaluation and the short instructions. Okay. We are taking as a simple push A, push B, add and pop. Like this simple instructions I am taking here. And what is the disadvantages means a stack can't be randomly accessed. This makes it harder to generate efficient code. The stack itself is accessed every operation and becomes a bottleneck. So it is somewhat difficult to add this one. Why? Because we are taking more number of registers and more push values and more instructions we need to do this one, and it is somewhat slow compared to other. And accumulator, okay, it is somewhat better compared with stack and short instruction. Okay, we are taking the short load A, add B, store C. We are not taking multiple operands, multiple operations. Okay, I am taking only simple operand and simple operators. Okay, so another one is a general purpose register. Okay, it is compared to stack and accumulator, it is somewhat good. And what is the GPR advantages means? Makes code generation easy, data can be stored for long period in registers. And what are the disadvantages means? All operands must be named leading to longer instructions. So it is somewhat better with stack and accumulator. But what is the disadvantage means? We have to take first load value, after then add value, add with the loading value and storing in C. But every time we have to call function of R1. Okay, you can observe here, first one load R1 comma A means we are calling a register value storing in R1 and add with R1 with B value, and we are empty the R1 value, then store R1 comma C means the result of C value is storing in R1. Okay, multiple times I am calling the R1 function for more number of operations. Okay. So each program is a sequence of instructions. The basic computer system, each instruction is subdivided into 4 phases. Fetch an instruction from memory, decode the instruction, read the effective address from the memory, and the instruction has an indirect address, and execute the instruction. Okay, these are the continuous identification of fault instruction. Okay, so in the program sequence of instruction, the basic computer system instructions are subdivided into 4 phases. Okay, fetch an instruction, we will discuss one by one. Fetch and instruction from memory, fetching, decoding, and read the function and execute. Okay, first fetching, where the value. Next decoding means we are converting from one to another, high level to machine level, like this, and read the function and execute. Suppose fetching means I am taking as a high level language. This I am converting to the machine language. This converting to the read function. Okay, and execute. Read means we are running, executing, and we are executing. There is no errors means we will get the output. So these instructions are subdivided into fetching, decoding, and reading and executing. Okay. So fetching and decoding. Initially, the program counter is loaded with the address of the first instruction. AR tends to PC. And IR tends, instruction register IR tends to M of AR. M of AR means address register, memory of address register. Okay, in the particular memory, the address I am specifying the particular memory. Okay, M of AR means in the particular memory, what is the address? That is a M of MAR. And PC tends to PC plus 1 means program counter is to PC plus 1. Suppose I am taking program counter is 0, 1, 2, 3, 4 like this. Okay, now PC is equal to 1 means 1 equal to PC plus 1. Okay, here PC will be there means 2 equal to PC plus 1. 1 by 1 it will be adding. Okay, last one what will happen? It will be go to the PC. Okay, so it is a fetching and decoding. It is a block diagram of fetching and decoding operation. So T0 and T1 I am taking, S0, S1, S2 are the bus, and these are the 3 inputs, switch S0, S1, S2, and I am taking the memory, read, address register, program counter, and instruction register. Okay, these are the very important for the input to output. Instructions are giving and PC, program counter, and address register. Okay, finally it will connect it to the bus. And the in the above diagram, the T0 equal to 1. Program counter of the bus maybe making the bus selection into S2, S1, S0 like a 0, 1, 0, S2, S1, S0, 0, 1, 0 like this. And if T1 equal to 1, it will be enabled as a read, and T1 equal to 0 means it is a write function. So determine the type of instruction. After executing the timing signal, T1 the control unit determines the type of instruction that is read from the memory. Okay, I am taking as a D0 to D7. Okay, if I am taking D7 equal to 1, the instruction must be registered as a reference input output. D7 equal to 0 means the operation code must be one of the other values. Okay, so it is a block diagram of simple instruction set. First one I am taking as a SC tends to 0, means AR tends to address register, program counter equal to address register. Already we discussed M of AR. So address register to program counter. PC plus 1 means next address, like this. Okay, if I am taking PC plus 1 means I am going for the next address register. So instruction register is M of AR, but means in the address register, what is the memory of address register to the instruction register, PC to PC plus 1. After the decoding operation, we know that what is the step 1, first one means decoding, fetching, decoding, read, execute. So T1 is completed, first time pulse, second one, after if D0 equal to D7 equal to 0, memory is a reference, D7 equal to 1 means register or input output. It will go to the memory, either memory or register. Okay, input output equal to 1 means it is executing. If it equal to 0 means executing with the register reference. And if it is an indirect function or direct function, direct means directly it is executing. If indirect means M of AR tends to memory of address register to the address register, it is executing as a memory reference instruction. Okay, these are the references. Okay, it is about the simple instruction set architecture. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.